Wait class ha. Wait class ha. I can't find in my... The sample problem cannot be shared. Wait. Why is it not? Wait class, I need to close Windows here. Okay. Can you see my screen?
Yes, Miss.
Okay, so we're now on this sample problem. I had so many files need to close. I can't find it anymore to be shared. So we have here a rocket engine that burns a stoichiometric mixture of fuel. So the mixture is that of liquid hydrogen and an oxidant liquid oxygen. So it's all liquid for this hydrogen and oxygen. The combustion chamber is cylindrical and it is 75 centimeters long and 60 centimeters in diameter. And the combustion gases produced in the process is 108 kilograms per second of exhaust gases. If combustion is complete, we are to find the rate of reaction of hydrogen and oxygen. The problem is asking for us to find the rate of reactions of hydrogen and oxygen, meaning it's asking for two things: the rate of the reaction of hydrogen and the rate of reaction of oxygen. And since we have these two in liquid form and it's undergoing the process of combustion, so I'd like this particular problem solved interactively. What do you think will be the stoichiometric equation for that matter that will guide us in finding the solution for this problem? What should be our stoichiometric equation that will guide us in solving this problem? So I need to go to the board. So you're given, in this case, so you have, as stated in the problem, what do you think would be the given information that we will write here? You have your reactor. So I'd like to start with the reactor. What is the given with the reactor? You need me to share again? What about your reactor? So you have a cylindrical combustion chamber. That's your reactor, 75 centimeter long and 60 centimeters in diameter. So 75 and 60 for length and D. And you have this amount of combustion gases produced. So we will need to write this. I think these are the things that are given in terms of quantity. And of course, it's specified that the liquid hydrogen and the liquid oxygen is to undergo the process of combustion. So I'll go back to the board and let me know how would be answer. So in terms of your reactor, it's a cylinder. The volume is of course unknown, but you're given that the length of the cylinder is 75 and the diameter is 60. This were stated in the problem. Okay. And then what else? You are given that your combustion gases has this rate of formation. So you reacted liquid hydrogen and liquid oxygen, and you have this combustion gases rate of formation. Now, these are the given information. Now, in terms of the required, what are we required to do? We are to find the rate of reaction of hydrogen and the rate of reaction of oxygen. Now, both are reacting species or substances, so this should be negative. So these are your required information. Is there anything that you'd like to add to this? So it's going to undergo combustion. The interpretation of the combustion of liquid hydrogen and liquid oxygen would be what? How would you write it down here? In terms of a chemical reaction, combustion, hydrogen and oxygen, how should we write this one?
H.
So that would be,
H2.
so we
H2.
have H2 plus O2,
One.
okay, forming, of course, your combustion gas is water vapor. Nothing will form out of the process of the chemical reaction combustion process of H2 and O2. So you need to balance this. This has to be 1/2. Okay, that way your atoms for hydrogen and oxygen will be balanced, bringing us a reaction which is, if you multiply by 2, that would be 2H2 plus O2, forming 2 moles of H2O. The stoichiometry will be our guide as to how are we going to determine the rate of consumption or the rate of change of the number of moles of hydrogen and oxygen. Do you have any question to what was written here? None? So if there's none, so we will wait. So we will continue. So if it's the rate of reaction of hydrogen, and if we are to start with the given, and that's the rate of production of water vapor out of the combustion, this is actually 108 kilograms specifically of water vapor per second. Okay, your combustion gases out of the combustion reaction of H2 and O2 is water vapor. So this is it. This is actually the given. And we will start with this. Now, what will be my next step here? I have it expressed in terms of mass per unit time. What will I do with this mass per unit time thing? You will?
Mole per unit time.
Okay, you need to convert this into moles. That way you can use the stoichiometric relationship in your chemical reaction. So there's a need for us to divide by 18 kilogram H2O per mole, 1 kilomole H2O. Okay, so you get to cancel the kilogram H2O. And then what happens next? You use the mole to mole relationship in your chemical reaction. So in terms of relating water to hydrogen, you could see that 2 moles of hydrogen produces 2 moles of water. It's just like 1:1. So you can have 1 mole H2O for every 1 mole of H2. Now you have successfully converted the given, which is in terms of H2O, to H2. So this is now mole H2. Specifically, that would be, we'll make this kilomole, and this is also kilomole. It's just the same thing, or mole. Anyway, the unit that would still be, after this, after cancellation of units, the units that will be remaining is kilomole H2 per second. Okay? There's no need for us to, okay. Where's my pen? Stupid. So yeah, it's draw weight class. Have you used this clipboard before? How do I switch to the pen? Oh my. I erase it. It's still eraser. Left. Okay. Can I still write? 1. I can't write weight class. It's draw. I changed to eraser and I can't write anymore. Select weight class. I'll have a new share. Weight class, huh? Let's see. It's still the same thing. I'll use the Jamboard. Weight class. I'll close that for now. Share screen. Let me see. It's still the same thing. Can I write now? Okay. Okay. So I have, why is this? Okay, 1 mole H2 to 1 mole of H2O. Now, the unit that is remaining here is kilomole H2 because we get to cancel this, the H2O and H2O here. So kilomole H2 per second. And if it's rate, it has to be expressed per unit volume. And since your liquid hydrogen and liquid oxygen is placed inside a cylindrical reactor, so you need to solve for the volume of the reactor, or simply the volume of the reaction mixture. Or that would simply be the B. So that would be your pi d squared over 4 times the length of the reactor rather. So you have pi times the d, which is 60 centimeters. We square it. And then you have here divided by 4, and we multiply by the length, which is 75 centimeters. You can have this converted if you want to cubic meter. So what is the answer here? Pi times 60 squared times 75 divided by 4. And somebody provide the answer? What's
0.212.
again?
0.212. 0.212 meters squared.
Okay. So you have 67,500 pi. This is in cubic centimeter. So if you'll change to cubic meter, we'll have this raised to 3. We divide by 100 cube. So that would be 0.212 cubic meter. So the rate, so you have already this, what's the answer here? This one will need to be divided by this volume here to make it the rate of consumption of hydrogen. So in this case, we need to divide by 0.212 cubic meter. And you will have the corresponding rate of consumption of hydrogen. Yes, that is the rate of consumption of hydrogen or the rate of disappearance of hydrogen. So you have 108, you divide it by 18, and you divide that by 0.212. That should give you 28, 28.30. So this would be mole, or rather kilomole H2 per cubic meter reaction mixture or reactor per second. Now, in determining the rate of disappearance of oxygen, you don't need to come up with this and start with this again. All you have to do is use the stoichiometric relationship. So that would mean that you use the balanced chemical reaction. So you have the rate in terms of H2 divided by the number of moles of H2 in the stoichiometric equation, that would be 2, or that's your chemical reaction. And then you have the rate of consumption of O2, and this one is just 1. Now, where am I getting this? It's taken from this one. So 2 is to 1. So your answer here, which is 28.30, all you have to do is use that in here. So 28.30 divided by 2 will give you the rate of disappearance or consumption of oxygen. So if you divide it by 2, so the rate of consumption of oxygen is 14.15. Okay? And that would be kilomole O2 per cubic meter reaction mixture per second. This is your answer for this problem. The rate of consumption of oxygen and that of hydrogen. So you don't need any knowledge, specific knowledge of expressing rate equations in detail, or um, kinetics in detail, because all you need to know is the stoichiometric relationship and the things that have been discussed in this chapter in your textbook. So this is in terms of this particular sample problem. Okay, now our second sample problem, I'd like to go to that, talks about the human being. So a 75 kilogram human being consumes 6,000 kilojoule of food per day. Assume that the food is all glucose, and that, of course, glucose is converted in this reaction, forming CO2 and water, and you have a negative rate of reaction here, which is 28.16 kilojoule. Find the man's metabolic rate, so the rate of loving, living, and laughing in terms of moles of oxygen used per cubic meter of person per second. Okay, so your given in this problem will be, of course, the mass of the human being, the amount of food that it consumes, and this particular stoichiometric equation. So we need to write all of this in our solution. So the given, so let's start with the given. So for number 2, they have the mass, which is 75 kilograms. And then the amount of food. So in terms of the energy that it contains, so I'd like to write here the amount of food that it's using, energy content of the food that it's using. So you have 6,000 kilojoule. And then you're provided with the chemical reaction of glucose. So in this case, C6H12O6, okay, we'll just balance it here. And 2816. So I recall that particular amount of energy, 2816. So in terms of your reaction, the problem already gives that to us. So C6H12O6, okay, then this will form CO2 and water. Now you have reaction, the heat of reaction is 2816 kilojoule. Okay, so if we need to balance, we will have here a 6, a carbon, and your hydrogen is 12, so we will have a 6, and no, 12, so we will have another 6 here, and your oxygen is, so you have 12, 18, 6, so you will have a 6 here. You have 6, 18, so that would be 12, 18. So this would be our balanced chemical reaction. You are required to determine the man's metabolic rate, and it's expressed in terms of O2 consumption. Let me go back to the problem so you get to see that its metabolic rate, the person's metabolic rate, is to be expressed in terms of moles of oxygen per cubic meter of person per second. So we'll have to write that correctly in our required information. So moles O2 per cubic meter of person per second. Is it per second? Okay, it's per second. So now we go back to our problem. We will still start with the provided information. So the provided information in the problem is that the food is going to supply 6,000 kilojoule of energy to the person if the person is going to consume it, or meaning the daily intake of the person will be able to provide it with this much of energy, 6,000 kilojoule. And if all those food are assumed to be glucose when reacted with oxygen during the metabolic process will have this particular amount of energy, 2816. So now let's go to our solution. So if I'm going to ask you, you will start with the rate of consumption of O2. You have to write it that way. So negative because O2 is being used up by the human being. And then you are to start with the provided information that daily, so that would be daily, the person consumes food which is able to provide him with this much of energy. So 6,000 kilojoule per day. So we'll write here day. Okay? That's the daily consumption of the person. Now, kilojoule. Where will I connect it in terms of the stoichiometric equation provided? So the stoichiometric equation provided tells you that if glucose is converted into CO2 and water in the metabolic process of the person, was that 2816? 2816? Why did I go back to that? I have also it in the given. So 2816 kilojoule. Now I need O2. So then I go back to my stoichiometric equation and I have here 6 moles O2. 6 moles of O2 when reacted with glucose present in the food of the person is able to liberate this much of energy. So then I can use that information. So I'll have here 6 moles O2. 6 moles of O2 reacted with glucose would produce this much of energy. So now I have converted that one, right? And that's it. You have to convert the day to seconds. So a day has 24 hours. So you solve this problem using stoichiometry and dimensional analysis. And 1 hour has 3,600 seconds. Now this takes care of the unit for rate, which is moles per second. It says there that you are to express it per cubic meter of person. We have to have an assumption because we are given the mass of the person, and that mass of the person, I like to write here, that mass of a person, which is 75 kilograms, can lead us to its volume, because our reactor is the person itself, because that's where the reaction actually happened, the metabolic reaction happened. So we will assume that since the human body is 70% water, it's okay to assume that we don't have the density of the human person provided in the problem. So we'll just assume that since it's mostly water, it's like water. So it's 1,000 kilogram per cubic meter. This is the density of water. That way you can convert the mass of the person to volume, which you can use here. So you have now 0.075 cubic meter of person. Then you place it here. So 1 over 0.075 cubic meter. Now you have the answer that we're trying to find. The man's metabolic rate represented in terms of its O2 consumption would be the 6,000 times 6 divided by 2,816 divided by 24 divided by 3,600 divided by 0.075. This will have 1.973 times 10 raised to negative 3. So mole O2 per cubic meter of person per second. So this is the man's metabolic rate. The rate of laughing, those things that were mentioned in the problem. So all of those things the man cannot do unless he consumes oxygen that keeps him living, or that keeps us living. So this is the answer to the problem. And I think the solution to this are also provided in the textbooks. I'm just redoing it here for you to have a clearer picture. So the examples that were given in this slide actually are classic examples wherein you can still solve a problem concerning kinetics. So this is not primarily chemical reaction engineering with reactor design for now, but a simple problem which uses stoichiometry and these two problems, stoichiometry and dimensional analysis, and you're able to solve for what the problem requires. And this are actually the starting points that the author of our textbook used. Okay? Illustrating how kinetics can be illustrated into a day-to-day observable phenomena and something that has something to do with combustion of fuel. Okay, now I think you may have questions here. You have any questions concerning the problem? Any question? Okay, so if there's none, I'd like to go to the new slide. So this would be the end of this slide. I hope you have already, some of you already browsed through what I made available in Canvas. Anyway, the due dates are placed in there. So read all the announcements and read everything there. Just ask me questions if there are things that are not clear. So I'd like to go to the new set of slides. I'll stop sharing for now. So after the overview of kinetics, what concerns it, we are now ready to go to kinetics of homogeneous reactions. I can't still find it here. Can you see the new set of slides? This is now module 2, kinetics of homogeneous reactions. Can you all see it?
Yes, Miss.
Okay, so we'll proceed. So in here, we'll be talking about the ideal flow or contacting patterns in the 3 commonly used reactors as basis in designing actual reactors in the industry. So for kinetics, our reactor to use, or the major reactor that is being used in analyzing empirical data is the batch reactor. So for this reactor, you are to, of course, you will have this correct assumption that the composition at any point inside the reactor would be the same, but that particular composition changes with time. So that's in the case of your batch reactor. Now, in the case of the steady state flow reactors, or simply the flow reactors, this one is the plug flow reactor, and this one is the constantly stirred tank reactor. Now, they are flow reactors. And in the case of the PFR, or the plug flow reactor, the fluid passes through the reactor with no mixing of earlier and latter entering fluid, and with no overtaking, as if the fluid moves in single file through the reactor. So there's no mixing that will happen. It simply is an orderly flow of the fluid volume inside this conduit, or this particular pipe, this tube. Now, in the case of the, rather, in here in the plug flow reactor, at any point in the tube or in the plug flow reactor, we of course have to understand that the concentration changes. It's because the reaction proceeds as the volume of fluid passes through the tube. So the concentration at any point will not be the same. Unlike the batch reactor, in at any point the concentration is the same. In the plug flow, it's not. In the case of the CSTR, or the back mix reactor, the concentration anywhere is kept uniform by the stirrer. So anywhere here, the concentration is uniform. So it's uniformly mixed. And however, the concentration, of course, of the reacting species as introduced into the reactor, and of the products and the remaining unreacted reaction species as it leaves the reactor, of course, will not be the same. But you have to understand that the reaction mixture inside the vessel at any time and the fluid leaving the vessel will have the same concentration. So concentration inside the reactor at any time will be the same as the concentration of the effluent, or the fluid that exits the reactor. This is in the case of the CSTR. But anywhere, the concentration is the same. Now, in the previous slide, the author of our book started with the representation of the rate equation because he used the presence of the derivative. Now we go to the rate law. Now, Chem tells you that the rate law is simply as simple as this. No derivatives to look into. You simply have a product of 2 terms. Now, in the rate law, you have the temperature-dependent term, which is your rate constant, the K, and the concentration-dependent term. Of course, it's already implied that it will have the concentration of the species. Specifically, the concentrations that you have here are the reacting species concentration. So the temperature-dependent term is the rate constant, and the concentration-dependent term, of course, will be the concentrations that are being multiplied, or the concentration of the sole species if it has only one reacting species. Now, the rate law gives the relationship between the reaction rate and the concentration, or the reaction rate constant K and the concentration. You still have the R here on the left, and I have written it as negative, meaning this A, which I use as the basis for my rate of reaction, is a reactant because I wrote it here as negative. And the rate law is written in this manner. These concentration terms are raised to an exponent which tells you of the order of the reaction if the reaction is elementary. If it's not, it has no bearing as to what numbers are these concentration terms raised to. We will go to that in detail later. But we will just focus on the specific reaction rate, or simply the reaction rate constant, and that is K. During our orientation, it's part of the topic in midterm that we are to look into the temperature dependency of the rate of reaction based on Argenio's, based on the collision theory. So we will now look into first the Argenio's equation. This K that you see here in your rate law is actually solved using this formula, A e raised to negative E over RT, where this exponential function has the argument negative E over RT. E being the activation energy of the reaction, the R the universal gas constant, the T written as capital is your absolute temperature, and A is your frequency factor. This frequency factor A and this K, of course, if you are to look closely onto our formula, will have the same set of units because your exponential function here is dimensionless, meaning the activation energy unit and the unit resulting from the product of the universal gas constant and the temperature has to be the same, or they have to be the same. So the unit of the A and the K are to be the same. Now, if you recall our discussion a while ago in the problem, you have this very fundamental relationship between rates of reactions expressed in terms of the species that are present in that particular reaction